that are mostly true. Dear Father, we thank you for this day. And again, Lord, thank you for your students. Just ask you to bless this work we're about to do today and just help us to glorify you in what we do, Lord. In your name I pray. Amen. All right, so today I was going to try to talk about how the primary the structure theorems of finitely generated modules over PID, how they play out in the context of an endomorphism, a linear transformation, right, of a finite dimensional vector space. So we're looking at, hopefully, the application of modules over PID, finitely generated. Modular PID to, let's see here, T going from V to V, where T is an element of the endomorphisms over V, where V is finite dimensional over F. In other words, the principal object of study in Math 321, right? So, looking at a linear transformation on a finite dimensional vector space, what can we say about that using the structure theorems that I discussed with you guys last time? So really, we're going to end. And so let's see, I think the first thing we need to do is remind ourselves, what is the module we're working with? We're working with M equal to what we usually call V, with the ring being polynomials and X. And what was our ring action? We had f of X acting on V equals to, what was it? F of T, V for all f of X in the polynomial ring, and V in V, right? And we discussed another day that this is far from a free module. In fact, this module is pure torsion, right? We usually discuss all of this by just saying V upper T like that. Although, if you look at, I think in Roman, he uses typically V lower tau, because his whole discussion is for tau, and he puts the T. I mean, the notation is not universal, right? I mean, there's definitely room for, there's no standard notation, okay, as far as I know. But anyway, so what did we say? We said that we discussed before that this fx module is pure torsion. How do we prove that? You guys remember? I think you're thinking of your homework, which is good.
Oh, isn't that what it is?
Yeah, that is the pretty standard argument. You could say, oh, okay, well, if the dimension over the field of V is equal to n, then this thing is n squared dimensional, right? So if you look at the set, how's it go? Well, T squared, T cubed, and I guess we could throw in the identity down here. T to the n minus 1, T to the n. What can you say about that? Assuming T is not the identity transformation, of course. I think if T is the identity transformation, then we can write a specific. I can write down the annihilator for the module. If T is the identity, then the module's eliminated by, excuse me, the annihilator of M is just x minus 1 if t is equal to the identity, right? Oh, I meant to write n squared. I'm sorry. But no, we don't. But for this rather naive entry-level calculation we do, I feel like this is one of your homework problems. But that's a chance I'm willing to take after I give you a lot of homeworks. But yes, the point of this is that we're in an n squared dimensional vector space. This has how many? N squared plus 1, right? So what's that say? That means that there's some linear dependence, right? There has to exist, C sub k in F, not all 0, such that, the sum k, n, j, some j equals 0 to k. I'm an idiot. J equals 0 to, I will eventually figure it out. K equals 0 to n squared of c sub k, t to the power k, with the understanding that t to the 0 is the identity. That is equal to 0, right? There's a linear dependence amongst these vectors, which are operators, of course. And so you can solve for that, right? Pick your, whatever non-zero coefficient there is in there. And this pretty much, I don't know, let's say C sub n is not equal to 0 for n largest, right? Then you could write that t to the, well, anyway, let me shut up. I don't even need that. I don't even need that. Don't even need that. Don't even need that. That already says that. So supposing that this is, g of t, right? In other words, that g of x is equal to c0 plus c1x plus plus ckx to the k. Since this is an identity, an operator identity, it follows that we have, g of x v is equal to g of tv is equal to 0 for all v and v, which is to say what? Which is to say that this polynomial annihilates everything in the module. So this proves that g of x is an element of the annihilator of M. Right? So the annihilator is non-empty. Yeah, it's not 0. But of course, this is an ideal in where? Of this, right? Which is again, a PID. So it follows then that there exists a smallest order polynomial in there which generates it, as we've discussed, right? We studied the polynomial ring last semester. We came to the understanding that the polynomial of least degree in an ideal of fx is the generator, right? By the division algorithm. So, in fact, definition, if M of x is monic polynomial of smallest degree for which M of t equals to 0, then M of x is minimal polynomial. For t. And the thing we just worked through proves a little, proposition, theorem, whatever you want to call it, proposition, of course, the annihilator of M is the principal ideal generated by M of X. Now, there's a really slick, sort of in-your-face obvious argument on page 472 of Dummett and Foote as to why this is pure torsion. So basically, what Dummett and Foote's argument is, so suppose, I mean, well, I mean, I showed this directly shows it's pure torsion because I've just showed that every, what? What does it mean to be pure torsion? It means that there's no, I mean, I guess one way you could say it, it means there's no torsionless elements, right? Every element in the module has torsion. So, I mean, otherwise, the torsion is the set of elements, non-zero elements which have torsion, right? Meaning what? How do we define tor? What was tor? What was the definition of tor M? Oh, I'll use M, that's fine. Like this? Non-zero R. That seems important, yeah. So, apparently, every vector is annihilated by this non-zero g of x. So everything is torsion. Right. But I like the argument on page, 472 of Dummett and Foote. He's like, suppose that the V upper T module was free, right, and had a Betti number, a free index, a free rank of one or more. Suppose it had some free portion. That would mean that there's a piece of V which is isomorphic to the polynomials, because every copy of R is a copy of fx here. But fx is infinite dimensional. So you can't have a free part, obviously not, because V is by assumption a finite dimensional vector space. It can't be isomorphic to polynomials. Or worse yet, pairs of polynomials or triples of polynomials, or however many pieces you got in the free part. So of course it's pure torsion. That's a nice little argument right there. And this is also too greedy, right? Because I mentioned to you guys before that we know more. In fact, it's eventually proved in this section that we have a Cayley-Hamilton theorem, right? And the Cayley-Hamilton theorem says what? Yeah, one way we could say it is that the characteristic polynomial of T is divided by what? The minimal polynomial of T, if you want me to. We could start adorning this with a T. That might be helpful in places like this. Yeah. But this also has other strings attached, right? Like every root of MT is also a root of char T. But what is the definition of the characteristic polynomial? Well, the definition of the characteristic polynomial here, which I haven't defined yet in this course, right? Where char T of x is equal to the determinant of x times the identity on V minus T. So here I make it monic. All right. Let's stop and take stock of things here. Oh, but I'm bearing the lead. What's the degree of this formula? This is nth order, right? Polynomial over f. So in fact, we can be confident that char t of t is the zero operator on V, right? Now, it takes a lot more work to get that result. It's just, basic linear dependent stuff to do what we did at the start of the lecture today. Just take n squared plus 1 vectors in this n squared dimensional vector space. You have necessarily linear dependence, but actually that's very, very greedy because, in fact, there exists for any linear transformation on a finite dimensional vector space the characteristic polynomial, right, which annihilates everything. But even that's too much in terms of being a generator of the annihilator of the module, because sometimes we can do it less, right? So how does this tie together with the structure theorems I was telling you last time? Like, what's the significance? Do you remember what the annihilator of a finitely generated torsion module was? How did it go? We had these like D1, the invariant factor form, all right, that's what I'm talking about. The invariant factor form, we had the D1, D2. How did it go? Just reminder is, D1, D2, DM, and I think that DM was actually the annihilator of the whole module. And by the way, Roman is very careful, but sometimes at the end of his theorems, he'll say things like you can test for the modules being isomorphic if they have the same this or that. He is under the assumption that those are torsion modules, right? I think they sometimes get lost in like the fifth part of the theorem or something. He'll drop that statement, and it's kind of important because you cannot. If two modules have the same annihilator chains, but they have different free parts, they're not isomorphic, right? It needs both the free part and the torsion part to match up. But anyway, so the annihilator is that, right? And what is the up to isomorphism? M is isomorphic to what? It's isomorphic to, how does it go? R, am I doing this wrong? D2. Right? So here, how does that look? Here, that looks like V is isomorphic to Fx, right? Mod the, ideal generated by, let's say, D1 of x. I'm just going to put it of x to remind us that we're quotienting by, here m sub t of x. That's the invariant factor decomposition of the vector space based on what? And what's the other thing we can say about this D1 through DM, D1, D2, dm? What was the other bit of the structure theory? They have to divide this. They have to satisfy this divisibility relation, right? But there's something else. How do those relate to the invariant, the elementary divisors, right? So this is the invariant factor form. What was the elementary divisor form? So remember, I mean, I can tell you this much. Elementary divisors. If we take the product of all those, right? So the product of all elementary divisors, what did we get? It's also equal to the product of the d1, d2, dm, right? And we talked about how you take the list of elementary divisors that sorts out through the different piece of I primary components, and you pick off sets of them to form the invariant factors, right? Do that systematic process we talked about last time. So, but the larger point here is that the product of all the elementary divisors is also the product of all the invariant factors. What is that for this module? Well, it's what? Is it the order? No, I think the order of V is the minimal polynomial, which is unambiguous here because we make the assumption of monic. So that ambiguity of associate last time, that washes away because we have the choice of monic polynomials, right? The associates of a given polynomial are all possible non-zero multiples over the field, of which there's only one monic. So it's an easy, natural, unique choice for that associate class. No, actually, what happens, what ends up, so this is the significance of the characteristic polynomial. The characteristic polynomial is the product of the elementary divisors. So that's what the characteristic polynomial is as it relates to this story. So this is actually the product of all elementary divisors. Now, when the characteristic polynomial is equal to the minimal polynomial, then T is said to be non-derogatory. I can't spell that. Non-derog. Okay. Spelling to be found in Dumb and Foot. Sorry, my bad. Okay, so those are some of the big pieces here, right? So great, but I mean, I think you guys all know how to calculate a minimal polynomial if you think about it, right? I mean, for a small enough example, well, let's see what my starting point would here be. For an actual example, what would you do? Right, calculate the characteristic polynomial, factor it, and then start trying to, find the smallest powers of those powers, which when you plug the matrix in, you get 0, right? That's one way you could do it. Just by explicit computation. It ain't pretty, but you could. So what Dumb and Foot doesn't talk at all about here, as far as I can cipher, maybe it's in the exercises, is how to actually find, well, they do and they don't. I mean, they describe a method of finding the basis which puts the matrix of the linear transformation in what's called rational canonical form. So rational canonical form is, what that's going to be is if you choose a basis for V, which respects the invariant factor decomposition, right? And then you look at the matrix of the linear transformation as it respects the invariant factor. I said something offensive. The invariant factor decomposition, then that's said to be in rational canonical form. Now, from linear algebra, we know that if we have the direct sum decomposition of T invariant spaces, by the way, any of these cyclic submodules are T invariant. In fact, when you look at what does it mean to be a submodule of this V's upper T module, one of the things you figure out very fast is that means that you're looking at a subspace which is closed onto itself under the action of T. So submodules are the invariant subspaces. But invariant subspaces in linear algebra are also the ones that if we have a set of independent invariant subspaces, then the matrix of the linear transformation, when you look at the matrix of it with respect to a basis which respects that direct sum decomposition, then you get block diagonal, right? So given that T invariant subspaces, all right, if we can make a basis, right, that respects that, then each part of the basis will give us a block in the matrix decomposition. And so essentially, all we really need to figure out to see what such a matrix looks like is, what does one of these things look like, right? Like what is, if you have this kind of thing, what's the matrix look like in that? And it turns out basically you get what's called the companion matrix of one of these pieces. Let me go through some calculations to support that. All of this said, like that, I'm struggling here because I'm pretty sure that the generalized eigenspaces play another role in this story that I don't see the word, he doesn't really talk about generalized eigenspaces in this section. The connection's not been explicitly made, but let's see here. If the week had more time, it would be wonderful. Let's see here. So I'm torn, you guys, between talking about what's in Dummett and Foote and just trying to work out here on the fly what the role of the generalized eigenspaces is. Let me look at the generalized eigenspaces for a bit, actually. That's the thing, is the notion of generalized eigenspaces is in general. Because the notion, what is generalized eigenspace? In case you forgot from linear, I used like k sub lambda for this. This was the, or you didn't have my linear. This is the kernel of, for me in my stupid linear, t minus lambda times the identity force. And this is where I forget what I did exactly, but something like this to the power p. I'm not sure that's. Is that? I can define eigenspace for you without ambiguity. I think it should be this. If I had to, all right. So I think it would be v and v, such that there exists p in the natural numbers, right? Such that t minus lambda I identity to the p-fold power acting on v is equal to 0. So that basically would say that v is either plain Jane eigenvector, or if you have that it's non-zero for p equals to 1, but 0 for p equals to 2, that'd be a v would be a generalized eigenvector of order 2. If you had non-zero for p equals 1 and 2, but it was 0 at 3, it would be generalized eigenvector of order 3. But I don't know where that ends. I want to allow the highest possible kind of eigenvector for eigenvalue lambda. And I suppose you can define this space whether or not it's actually an honest-to-goodness generalized eigenspace, right? It's only going to be a generalized eigenspace for your linear transformation if lambda actually is a root to the characteristic polynomial. I mean, nothing stops me in general from calculating this space even if lambda is not an eigenvalue, right? It's just stupid, because if it's not an eigenvalue, this is just going to be 0. So, and then, of course, this contains the eigenspace with eigenvalue lambda, right? And of course, to be symmetric with my current abstract linear algebra, I really should write lambda I minus t instead, right? To be more in tune with our current characteristic and minimal polynomial. But old habits die hard. All right, so think about this. Well, anyway, this is a theorem. If the characteristic polynomial of t of x and fx is split, meaning that we have what? So in other words, we can factor, right? We can factor the characteristic polynomial into a product of linear factors, possibly repeated, right? Then here I'm assuming that these lambda 1 through lambda s is distinct for the sake of our discussion. In this context, you can prove. This is actually not a theorem. This is a definition at the moment. Sorry. I just defined split for characteristic polynomial. The theorem I want to say is the following. Good grief. If the characteristic polynomial, right, is split as above, then V is not isomorphic. It is literally equal to the direct sum decomposition of the generalized eigenspaces. I mean, this is what we ultimately come to in linear algebra. So, you see, I'm not working up to isomorphism here. I'm saying that you can actually find generalized eigenvectors which form the direct sum of V like this. And by the way, so what's the annihilator of like k lambda I? It's something like x minus lambda I, to some power p. So in the case, so I here M1, M2, MS, these are the algebraic multiplicities, you may recall. Algebraic multiplicities. In contrast, of course, we could talk about the geometric multiplicities, right, which would be the dimension of the eigenspaces. We prove what? We prove that the algebraic multiplicity puts an upper bound on the geometric multiplicity. I mean, if we were to say that the dimension of E sub lambda I was equal to, let's say, n sub I, we would have that n sub I is less than or equal to m sub I for all I. All right. So guys, you can tell me a little bit more here, though. If you look at this, so the annihilator, I probably should put a sub I here because it's got an I dependence, yeah. So think about this. What if you have distinct lambdas? Can you tell me what's the greatest common divisor of like x minus lambda I to the pi and x minus lambda j to the pj for I not equal to j? So what I'm doing right now, Kang, is I'm trying to break the vector space into a direct sum of generalized eigenspaces and discuss how that fits into this story of the primary decomposition theorem. I assert, and I haven't proved this, but I'm relatively sure what this is so in this context when it's split, that means that what you're looking at here, these are the prime factors of the order of M. This is p to the mi. This is p1 to the mi. This is p2 to the mi. This is p sub s to the mi. These are the primes. All right? And, well, prime powers. And I would argue that if these are distinct, if you have distinct eigenvalues, then these prime powers, what's the greatest common divisor? It's 1, right? These are relatively prime powers. I mean, in other words, these are distinct primes. X minus lambda I and x minus lambda j. These are distinct. And what that means then is that all of those beautiful formulas we read about distinct primes in the general decomposition are still true here. Like, what's a formula, for example? What's a formula for k lambda I? We could also write it is, how's it go? Dang it. I mean, there's all kinds of beautiful things that are true. For example, if you take the sum, right, I equals 1 to s of x minus lambda I to the pi, right? Well, you can pick coefficients c sub I such this is equal to the identity on V. You can build the identity operator as a sum of the annihilators, a weighted sum of the annihilators for each piece. And you can build each one of those pieces by like taking the characteristic polynomial and just dividing by the requisite prime power. These things are spelled out pretty cleanly in Curtis's linear algebra if you want to read more, like detailed more. All right, great. Let's see here. So I have failed at the moment to derive the companion matrix, and I think I'll leave that for next time. So I hope I've given you enough of a reminder of the things that we know from linear that you can start to piece things together here. I'll try to say more next class as it relates to this story, all right? But I wanted to get the ball rolling on something else today, which is the so-called Smith normal form. Because this, about half of the section in Dummett and Foote is on Smith normal form. And so what is Smith normal form, and what does that have to do with anything? Let's see if we can't just calculate the Smith normal form for a particular matrix. All right. Suppose we're looking at A equal to, and I actually wanted to do something that I was going to foolishly try something other than, I don't want to just do the book example because there's like one. So I wanted to do a different example. Come on. Oh. Anyway, I'll actually show you examples of rational canonical forms, like with numbers. Friday, I will have something to project. It didn't happen, unfortunately, for me. In the last 24 hours, my time got eaten. I mean, I did spend about 2 or 3 hours preparing for this class. It's just, this is where I am right now. It takes me longer for what we're currently doing. I'm looking for a 3 by 3 diagonalizable matrix. Do you guys happen to know one? Don't give me a diagonal matrix. Don't you even. Like, what am I even asking?
Diagonal matrix with 2 rows transpose.
You're the worst. Let's see here. I guess I should have expected that. All right, fine. This is slightly ugly. This may not be ugly enough to dang it, that's just not going to do it. Come on. See, this is the problem. You look in an elegant linear algebra book for an ugly example, you're just wasting your time. Because then they ask these questions like, if it's possible to diagonalize this matrix. Well, so I don't want to start on that, you know. It's no help. Curses. And then, of course, I got one written on a piece of paper in my office, which doesn't help us now. Oh, I think I found one.
Set up a big monitor in your office.
A what monitor? So here's a good example from Inzel, Spence, and Freeberg. 401 2 3 2 1 0 4. Okay, this I know is diagonalizable because I'm looking at the calculation of the eigenbasis right here. The eigenvalues are I think, what? 5 and 3. All right. So what is Smith normal form? What you do is, and this is the algorithm is more or less described in Dummett and Foote here. It's a method to calculating the Smith normal form will reveal for you the invariant factors. And once you understand this, knowing the invariant factors allows you to write down the rational canonical form for the matrix. That is not to say that you have explicit access to a basis which similarity transforms the matrix to the rational canonical form. But by the way, that's the larger story. If we have 2 different linear transformations and they have isomorphic V upper T modules, that means that the matrix of those transformations is similar. In other words, it's just different notation for the same linear transformation. But anyway, so this is the Smith. So the thing is, finding Smith normal form is a relatively straightforward calculation, which will reveal Smith normal form. Will reveal the invariant factors, but it won't directly tell you what the basis is that puts the matrix in rational canonical form. In contrast, if you calculate the generalized eigenchains, in the case it's split, then that gives us directly the basis which puts it in Jordan form, right? So it depends on what you're after. Now, Dummett and Foote explains through a laborious algorithm how you can basically stalk the algorithm for the Smith normal form, and in so stalking, create the vectors which form the basis, which puts it in rational canonical form. But trust me when I tell you, you can read it. I'm not going to try to describe how to do it. But that's actually a good thing to work through. I think it's better for us to work through it in the context of classifying finite abelian groups. So that's where I'm going to scratch that itch. All right. So Smith normal form. What do we look at? We look at xi minus a. All right, so xi minus a is what? So x minus 4, 0, minus 1, 2, x minus 3, minus 2, minus 2, minus 1, 0, x minus 4. And then it's a lot like just regular row reduction, except we're also allowed to do column operations. And, well, let's see here. Here are the rules. You're allowed to interchange two rows or columns. You're allowed to add an fx multiple of one row or column to another. And multiplying any row or column by a unit in fx, these are elementary row and column operations. So first things first, you look for the greatest common. So basically, the greatest common divisor here is going to be 1, if you look at all the entries. Since there's constants, it's 1. And so I would start by putting this over there. And I'll multiply by. Oh, fine, I'll just leave it. So, Kang, you want to tell me what to do next? What's that? So clear this out, right? So we get minus 1, 0, x minus 4. And so 0 and 0. Yeah, I'm going to do that. But I'm just going to do the first. I'm going to clear out below the 1 to start with. And so I add twice, subtract twice the first from that. So that's still x minus 3. And down here we have, what, minus 2. Minus 2 times x minus 4, right? And so to get rid of that, this has to be, what, row 3 plus x minus 4 times row 1, right? So, but that's the new thing. We can do polynomial times row, like that. And so that clears out this x minus 4. 0, 0, what happens here? And then here's the new, more fangled thing is you're allowed to do column operations. So you can take this one and obliterate that. And yes, so I would want to do what? Column 3 plus x minus 4 times column 1, right? And that makes that 0. That leaves this as it is, right? And leaves that as it is. This is the start of it. And then, of course, you rescale that to 1, and you repeat this process on the next block down. Eventually, after you're done with these kinds of steps, what you got is 1, a1 of x, a2 of x, like that. Now, I'm pretty sure what happens here is this will end up being x minus 3 times x minus 5, and this will be x minus 3. Oh, I think it actually works out to this. Because this is diagonalizable, which means the minimum polynomial is just a product of linear factors not repeated, because the geometric multiplicity must be 1 for each eigenvalue if it's diagonalizable, which means that the minimum polynomial is a product of distinct linear factors not repeated. And with that, we're done. Try to do more of this next time. I just wanted to get started on this idea. Hmm?
The last polynomial just equal to factor.
Well, that's a good question. Yeah, because I should have a product of, maybe this should be x minus, it's the 5 that's, whichever root's repeated, it's got to be up here, you're right, yeah. So this divides that, and that divides that. That's the minimal polynomial. There's your invariant factors. All right, so hopefully I'll have more examples of this to show you next time. Actually worked out to project, unfortunately. Like I said, not happy with where this lecture ended up. Just, as you know, life gets in the way sometimes.